In this problem, we're going to remove 4 aces from a standard 52 card deck. We'll shuffle those 4 aces and pick a random card out of the 4. The card selected is an ace of spades. So, can we draw a tree diagram for this probability experiment? And the answer is yeah, we can. Because the 4 cards have similar shape, um, it's conceivable that we have an equally likely chance of picking from those aces. So what are the possibilities? We could have an ace of clubs, ace of spades, ace of diamonds, and ace of hearts. So the probability experiment described is picking a random card given that the card must be an ace. What this describes is a new type of probability, a new type of idea. It's called conditional probability. And what it means is that we limit our sample space to only certain outcomes that meet a given criteria. Okay, now I can write this in symbolic form as the probability of drawing a random card and then I'm going to put a line there, a vertical line, which means in probability mathematics, it means given that the card is an ace. So the first part represents the action that you're going to take, but the second part represents the condition that was set, that it must be an ace. And we'll see that again in the future. Can a tree be drawn for the situation? Yes. And the sample space would be made up of the ace of clubs, ace of spades, ace of diamonds, and ace of hearts. Those are the 4 possibilities. And they said the card selected was the ace of spades. Okay, now can we draw more complicated tree diagrams where perhaps more than one action is taken? Here's a diagram for the tossing of a fair coin twice. Now, just like before, we're going to start on the left, and then we can take either the heads path for the first toss of the coin or the tails path. But regardless of whether that first toss lands on a heads or a tails, we're going to have to toss the coin again. And so from each of those, we want to create another copy of that same diagram. Notice that it's duplicated twice because of there being 2 outcomes to the first action, you know? So this part here, it gets repeated twice. And that will come up again in a thing called the fundamental counting principle. But anyways, what we want to do is we want to keep track of what happened in our path from the start to the end. Okay? So let's say the first time we flip it, let's say we take this heads path. So we'll color that in real dark. So the first coin lands on heads, in other words. Then let's say we flip it again, and we land on heads again. Then we would take this path. Now if we trace the path through and see what happened in both of the actions, first flip landed on heads, the second flip landed on heads, we want to write that down as an outcome to the overall experiment. In this case, it would be HH representing the first coin landed on heads and the next flip landed on heads too. Whereas down here, if we were to take another path, we could take the tails path, and then from there, maybe get a heads on the second flip. That'll take us to an outcome of TH. Tails for the first flip, heads for the second flip. As you can see, there are 4 possibilities, and let's look at which ones would be considered simple events and which are not. So a simple event is when there's only one possible way for it to happen. So it would be a single outcome found in the sample space. For example, the outcome where we get tails and then tails, that would be simple because there's only here one outcome in that criteria. There's no others like it in the sample space. Now, what about getting the same face of the penny to land up on 2 flips? Well, there's 2 ways to do that. You could have it land heads and heads, or tails and tails. So, there's 2 ways to do it. For that reason, it is not simple. But the particular outcome, heads, heads, is simple because it's more specific. What about the combination of exactly 1 heads and exactly 1 tails? Well, if we look at the tree, there are actually 2 ways for that to happen. You could get heads on the first flip, tails on the second. Or you could get tails on the first flip and heads on the second. So because of that, we're going to say that's not simple. Technically, they're permutations, not combinations, but we'll look at that later in a later video. Anyways, combinations used in the English language to describe that situation, so that's why that's there, I guess. What about tails, tails? Of course, it is simple. All right, let's draw a tree diagram for the probability experiment of a coin being flipped and then a 6-sided die being rolled. Find the sample space. All right, so I'm going to draw one from the top down. I'll start up here, and I'm going to go to 2 possibilities for the flip of the coin, heads and tails. But then from there, after I flip the coin, I need to roll the die. And so from that heads, I need 6 branches representing the outcomes 1, 2, 3, 4, 5, and 6 for the roll of the die, that is. And then I need 6 branches here on the tails. Now, in order to write the sample space, we have to imagine taking a path here and then completing the experiment by rolling the die. We're going to put them 2 together into a single outcome called H1. means a heads was flipped with the coin, and then a one was rolled. So if we do that process for all the different paths, we get this. Okay.